Okay, so good evening, everyone. So this is the sixth tutorial session on NPTEL course on computational quantum mechanics. And in today's session, we would be reviewing some the conservation laws, which are conservation of mass, linear and angular momentum, and Cauchy's stress principle. And then we would be talking about objectivity of tensors and talk about equilibrium equations and also a very uh, elementary introduction to the principle of virtual work. I will just, with regard to all these conservation laws, I'll just be specifically only mentioning the mathematical models, mathematical representations of. So broadly, it's just conservation laws. So there are 5 laws of mechanics. I mean, as was discussed during this week 6 of this course. 5 laws of mechanics. The first is law of conservation of mass. Conservation of mass. The second is law of conservation or even balance of, it's the same thing, balance of linear momentum. And then law of balance of angular momentum. And the fourth is law of conservation of energy. And then the fifth one comes, second law of thermodynamics. Although second law of thermodynamics is very much, it has a significant role or a very important role in quantum mechanics with respect to the design or even constitutive development of new constitutive models. And thing is, any constitutive model has to satisfy the constraints prescribed by the second law of thermodynamics. So, but in this particular course, as the instructor had mentioned that he would not be discussing, so yeah, we would not be talking about in this about the second law of thermodynamics and even the conservation of energy. Okay, so the first one is conservation of. We'll be discussing only the first 3. So which are these 3 we'll be discussing. I'll start with conservation of mass. So from the conservation of mass, it said that say if you have body B or body B naught, and say after certain deformation, it has assumed another configuration, which I'll call just B script B. Let's say time t, and there is a t is equal to 0, and this t is equal to some time t. Then the law of conservation of mass is that mass of B naught equals mass of script B. So for a particular body, the mass of the body will always remain conserved, no matter whatever the deformation it undergoes. So that's what it is, yeah. Okay. So what will what we'll do is in the integration in the integral form, this will come out to be integral over p naught rho naught as a function of x vector comma t dv naught is equal to p rho x vector comma t okay, dv. Now is what we had what we know from the previous class is that how the area or the volume changes after deformation, right? So dv is nothing but capital J dv, where J is the J is just the Jacobian. So which means that if once we put this back here, which we substitute it here, then it becomes v naught rho naught comma dv naught is equal to, and then it's as if we have mapped it to the reference configuration, right? So this becomes rho x vector comma d. Then I have to have x vector as a function of capital X vector comma t and j dv naught. Okay, and then what we can do is we can combine, bring both the terms on one side, and rho naught minus rho j, okay, and dv naught is equal to 0. Now there is a there is a theorem, I have just forgot its name, that it says that if this holds to be 0, and for no matter whatever the segment of the body is or part of the body is, it simply means that rho naught is equal to rho j, or the integrand is 0. That's what it says. Okay, I think it's known as localization theorem. Yeah. So from localization theorem, what we have is rho naught minus rho j is equal to 0, because this is the integrand of this integral. So, and then this is nothing but rho naught is equal to rho j, and this is what we call as the material form of conservation of mass. Okay. Now, let's talk about the other.
Krishna,
Yeah,
can you please put the last slide on? Yeah, just a moment. Just writing
yeah,
down.
yeah.
Okay. Yeah.
Sure, sure. Okay. So next, what we'll do is let's take what we had discussed in Reynolds transport theorem. So from Reynolds transport theorem, which is a very fundamental tool in quantum mechanics, in fact, the Reynolds transport theorem is nothing but something known as Leibniz integral. Leibniz integral theorem. That's what I think it's called. So it's just a consequence of Leibniz integral theorem. So from Reynolds transport theorem, what we have is, say, any integral, isn't it? The rate of change of any integrals. So you have integral I, rate of change of this integral, say d by dt of mm, b, say g vector comma t dv. This comes out to be d by dt then it just we do a sequence of steps after which we arrive at the fact that this is equal to g dot, which means the total derivative of g plus g vector or any g, and then divergence of v vector. V is nothing but the velocity field. Okay. So this is just what we know from the Reynolds transform. Now let's utilize this in this
Yeah.
particular
So
context.
I have one
Yeah.
question here
Yeah.
actually.
Mm.
So I mean, not a small question actually. So divergence of V is the
Mm.
unit consistent? I think why? Just wondering.
Yeah.
So
The thing
you
is,
take G. So
the divergence.
is G dot unit of G dot is that
Mm.
equal to G times divergence of V? I think divergence of V is like 1/time. Yeah, that's right. Okay. Okay.
Yeah. Actually, the thing is, divergence of yeah, it comes out to be per second.
Okay. Also, when you say divergence, um, so it's
Mhm.
like a volume integral, no? Like you take divergence at every point.
No, the thing is, divergence again. This is a local operation, isn't it? When you compute
Mm-hmm.
divergence of any vector,
Correct.
it's this this particular operation happens to be just around that particular around that particular what you call mm, point about which we are studying. So say if you have say we have this point x. So when we and say v vector is defined over here. So what we do is divergence is when we compute divergence. This it is also a local operation in that this particular area to which it's what do you call applicable. There is just some epsilon, something like a sphere of radius epsilon. So these are like local operations because ultimately divergence involves that the sum of partial derivatives in all the directions. So it's just like whatever holds for the derivative that will hold all those requirements are there for divergence as well. And I mean that we are talking what you are talking about that is actually used to link divergence of some quantity over a volume to that of the volume of the superficial or the super I mean the surface integration of that particular quantity. So that is what is known as Gauss divergence.
Yeah.
In that case, what we do is we have some particular volume. Okay, let's call it capital omega. Say we call it omega, and say some velocity. Sorry, some vector field is defined over this. Some vector field. Okay. So some vector field, we call it, say some uh, H vector field is defined at every point within this domain. Now, and provided that this volume is closed, in that sense that there is no discontinuity in the boundary of this volume. So then it simply implies that you can relate the divergence of this vector field volume integral to the surface integral ds. So this is what is I mean the thing is it was a very it is still I mean it's really very powerful tool in this which is used I mean developed by Gauss, right? So
Yeah. Yeah. Yeah.
to link any change in the entire body to the change
Correct.
at the surface. So that is that was the goal here. I mean just to link both up. So the way we use it here is uh, and Okay, so in Reynolds transport theorem we have this. Now is yeah, now you know that okay, let I is equal to m. Okay, so let I is equal to m. M is mass, and let G be rho. Then this the expression above turns becomes simply d m by dt is equal to d by dt of rho rho dv, and then using the full expansion of this, we'll just have b rho dot plus rho divergence of v vector to d. And you know very well that uh, that dm by dt mass from the conservation of mass, dm by dt has to be zero. So this becomes, isn't it? Now again from localization theorem, localization theorem,
Nice.
localization theorem, what you are able to say is the integrand itself has to be zero,
Yeah, and you
isn't
get
it?
conservation of mass.
Yeah. So this is what is known as the spatial form, spatial form of conservation of mass. And we also know that rho dot is defined as partial rho by partial t plus grad of rho, something like v dot grad of rho. After substituting this here, what you have is partial rho by partial t plus v dot v is velocity, v dot grad of rho plus rho of divergence of v vector is equal to zero. Now we know that the second and the third terms combined to give us rho by rho plus there is nothing but divergence of rho into v vector. So I think this is the form that we always in which the conservation of mass is usually written. This is the form, but ideally they is the same. This is what comes directly as from the from derivation, and this after substituting the total derivative in terms of the spatial and convective derivative, you can get this is a more compact form. And using this form, actually the thing is when you talk about a flow being compressible or a fluid being so there is I think we had discussed the last time that there is a difference between flow being incompressible and the fluid being incompressible. Isn't it? So for a flow to be incompressible, it simply implies uh, that the sum of the total rate of change of density plus the rho divergence of v vector is equal to zero. So this is when all of the terms. So I'll just tell you. So I think this is a very important. It's the incompressibility of flow versus what we mean. But let's bring both the cases here and also parcel t. Oh, so
Ah,
okay.
lock it. Lock it.
Yeah. Now what happens? Okay. Mm. So this here is local rate of change in time. So it's just like time derivative. And now what you see is the difference between this term here. This term is actually partial rho by partial t plus v vector dot grad of rho, isn't it? Yeah. Now So here actually is so this we can write as 2 minus rho of divergence of V. Now when we say that a flow is incompressible, it simply means that as it moves, so that as it moves, this entire term is zero. This the set of two terms. So it means that for incompressible flow, rho dot is equal to zero.
You mean the material derivative? Yeah.
Yeah, the material derivative
Yeah.
is zero.
Incompressible.
And you see that material derivative is equal to zero doesn't mean that there is literally no. I mean, the thing is, there may be change in density momentarily, but it will be compensated by that due to the convective the convective derivative.
This is actually something really good point to discuss.
Yeah.
As in, while I was doing my fluid mechanics course in my masters, even that
Yeah.
so he discussed all this stuff, and he
Mm,
said in the book it is given that even though the flow is incompressible,
mm.
there could be places where the flow is locally compressible,
Of
but
course, yeah.
overall it is incompressible.
Yeah, overall, it simply means that say this term can be negative and this term can be positive, and vice versa, isn't it? So which means that the effect of one is contracted by the other.
It
So
implies the
just
density is changing locally, it's not constant.
yes, yes.
But
So,
but when the particle is going from here to there,
yeah.
that's what we are discussing, right? From here to
Hmm,
some other place, the
hmm,
density is constant of that particular particle, but
hmm, hmm.
locally it is changing. Oh, this is
Yeah, yeah,
complicated, man. This is
yeah,
hard
yeah,
to comprehend actually. But anyways,
yeah.
okay.
So, so the thing is, it all boils down to this fact that it's always the how both the components of the change in density, how both of them combine to give a resultant effect. So it's all about resultant effect. There is, yeah, it's in an ideal incompressible flow, uh, both the terms has to be. So for incompressible fluid, isn't it?
Okay.
For incompressible fluid, this also has to be zero, and
Okay.
this also has to be
Okay, so there's a difference between flow and fluid. Like flow is like, so we're discussing the
exactly. Flow is,
mechanics, and
yeah,
when you say fluid, it's like it's just talking about the material itself.
right, right, right. So in this case, isn't equal to zero and isn't equal to zero. This is for flow, and for fluid, this is how it comes. Yeah, so that is the thing is because when we consider any I mean, when it's incompressible fluid, it means that there is nothing which can change its density. It cannot change in time. It cannot
Correct.
change as it
Correct. Correct.
progresses.
Yes.
So it means
But
that
flow
even
is
grad,
like we are saying it's a flow. So the flow can
yeah,
like we are dealing with flow. In the second case, we are dealing with the fluid like material. That's
right,
the
right,
difference. Yeah.
yeah.
Okay.
So the thing is, this is a very tough condition to actually be seen in nature. So we always go by this that okay, let's make some assumption and consider it to be
Right.
that the metric. Yeah. So this was the that, yeah. So now what we do is let's not talk about. Um, so based on based on this particular relation that we derive this relation here, uh, this it actually helps us to little bit extend Reynolds transport theorem. So say that we have an integral quantity of again just the same g as a function of x comma t dv b, and let's take g to be rho into phi. So now phi is some other quantity and rho is our density. Then what we have is then we have I is equal to rho phi dv, isn't it? And then once we take its material derivative, so it gives us uh, uh, the ones that we have talked about, right? So it just becomes B rho phi dot plus rho phi divergence of V vector.
So here like phi is
Some quantity
per mass.
Some
Right?
quantity, yeah, some quantity per mass, yes, yeah, per unit mass, right?
Very like okay.
Yeah,
Yeah, very confusing.
yeah. The thing is, this is the form of transport theorem that we tend to use everywhere. Ultimately, in deriving the
Awesome.
angular.
Great.
So what
Hey,
we
can
do
we
now is,
shall we derive this? Just that I mean, I understood you wrote it directly, like rho phi
huh,
dot plus rho phi divergence of V.
the thing is
We have
this.
derived it for the previous case. I understand that.
Yeah. Actually, the thing is here, you just have to put G is equal to rho phi.
Where can you go back and yeah.
Here. Put
Okay.
G is equal to rho phi, and here again G is equal to rho phi.
Okay.
So
So
it's
the rho
just
phi
that.
dot is
Yeah, so it's just like we are taking there is just overall dot acting on the product of two quantities. Now we need to use chain rule, and then we'll have rho phi dot plus rho dot phi, isn't it?
yeah.
Plus rho phi divergence of v vector dv. And this is actually volume, yes. So I think that's it. Now what we'll do is what we do is we see that there is phi coming here and phi coming here as well.
Correct. Take phi
So what?
common.
Yeah. So what we'll do is we'll take rho phi dot plus phi into rho dot plus rho divergence of v vector
That is
dv,
conservation of mass.
isn't it? So you see that this goes
That is
away.
zero. That is zero. Okay.
So
But
so that's
that is zero. Only if so here rho dot that a partial or is that a like material dot
this is rho dot is material.
zero by dt.
Yeah. In quantum mechanics, when we actually mention this dot, then it means total derivative.
Okay. So that is zero. Yes. Previously
Yeah.
we derived it
Yeah.
that full is zero.
Right. So which means that this expression has simplified to such a neat expression, just rho into phi dot into dv. And this expression is very powerful because this we use everywhere. Now, when you put phi is equal to v vector, then it becomes a rate of change of momentum.
Yes. Yeah.
And then if you put phi vector to be uh, sorry, phi to be some r
Energy.
cross v vector, then it becomes
Angular
moment
momentum.
of
Okay.
the angular moment. Yes. And when you and when you put phi is equal
Energy.
to small e, then it becomes total
Conservation of
internal
energy.
energy. So it all depends. So this is the form that is very much helpful to us. Yeah. But before that, we had to first derive that the conservation of mass holds. Then only we can. So it's like conservation of mass is the most fundamental conservation law. Then rest follows one after the other. Because had there been no conservation of mass, then this expression could not have been simple. Could not come out in this form.
So this rho dot. I mean, I know as in yeah, that's true. So it's like mass is always conserved, but so the point is, so I think irrespective of d rho by dt. So if it is incompressible, if you assume the flow to be incompressible, then
Hmm.
I think no. If you assume flow to be incompressible flow,
Yeah, this one is actually
so the net is zero. It's like we're not dealing with single quantities, so it is always zero.
hmm, yeah.
Okay, yeah. Okay, well, let's proceed.
Yeah. Now what we do is now let's go to the next part, which is balance of linear momentum. The balance of linear momentum. this case, what we do is we just have take P is equal to V vector, isn't it? Then what we have is and then we call as I to be L vector. L is what we call as linear momentum. So it becomes dl vector by dt integral of over b rho into v dot, isn't it? And then
dv.
dv, yes. Now you say that, so this is the rate of change, but rate of change of momentum is we need some external force, isn't it, to create
So Krishna, I have a
this.
small question here.
Yeah.
So so this rho times dv.
Hmm.
Okay. I thought that v dot is actually a quantity per mass, but it is not. Previously, we thought that.
Yeah, so that's why we
So,
say
so
that
v dot is just a quantity. Is not tied to any mass or volume now.
yeah, so it's so the thing is yeah, it's just some quantity per unit mass, some quantity. So then here we can, what can we call it?
But
So
here it
v
is
dot,
not no because if but here v dot is not quantity per mass, right?
yeah,
If you
the
understand
thing
what I'm
is,
trying to say.
yeah, the thing is we can call v vector to be linear momentum per unit mass, isn't it?
No, if you consider that as linear momentum per unit mass, but so the units of that when you multiply because the total units will be only okay linear momentum per unit mass.
Yeah. So
Okay,
then it
yes.
becomes
So
then it
yeah,
goes
so
away.
linear momentum itself is like yeah mass times that then okay yeah
Right, right. So the thing is now what
that
we
is
do
true.
is
Linear momentum per unit mass. Yes, that's right.
yeah,
Awesome.
isn't it?
Awesome.
So what we do is this term, so this is always the internal change uh, of the property of within a particular body B. However, that change has to be caused by some other external agency, isn't it? So that's why we always bring forth x vector here, fx vector, f external vector,
Yes, correct.
and this comes from the second or whatever second law of motion. Second Newton's second law of motion. Yeah. And in the mass, this was not needed external. The thing is because within a particular body, no matter how much we deform, the mass won't change. So that's why the term on the right was always zero. But for other cases, we have to have something which is producing the effect. So we club all that external influence in this particular f external vector. Now this can be what you call broken further down into two components. One is what we call as the rho into b vector, dv. B vector is the body force. It is body force. It has the units of acceleration. And plus the other thing is traction. T vector to ds. This acts on only on the boundary of. So this is what we call as the surface force. So there are these two forces in nature. Either it should be body force, which actually exerts or which yeah, which affects the entire body affects every material point within the body, and there is surface force which only affects those material points which are located at the surface of the body. So there is a this particular distinction between the two. Body force usually tends to be, for almost always, I mean it is force at a distance always. Force at a distance. So it involves gravity, electromagnetic force, nuclear force, name it. So all these are all body forces. However, surface force always required physical contact. So this involves pressure force, and if it's say any viscous drag or anything like that, or a viscous forces is also going to. These all come under they come under surface force. Even things like what they call in what happens in say photoelectric effect and all, right? It's always the what we call forces. They are applied only to the points or the material points which are lying at the boundary, isn't it? So there is a difference between. I mean, so we just have two types of forces: surface force and body force, or sometimes they're also known as volumetric forces. So
Yeah. So
there are
yes.
this.
Correct.
So now, based on this, what we have is we have been able to obtain the second conservation of linear momentum to be rho v dot dv is equal to rho v vector dv plus traction ds parcel. So this is what is the second law of or the conservation of balance of linear momentum. However, now the thing is, okay, this we have, it's done. Now here is what very important principle called as Cauchy's stress principle is introduced. The thing is, when you take a look clearly, carefully here, so this term, and this term, it involves it is applicable for every material point in the body.
So I have a small
However,
question, Krishna here actually.
yeah.
Um, Not about, I mean, about this, but kind of. So we're taking this material point, like material point. How are we defining
Hmm,
surfaces? This is a question I had like for a long time. How are we
hmm.
considering like the surface of a material point? Like we say that this doesn't exist, right? It's just a point. How can you define a surface?
No, no. The thing is,
And
no, there is no there is no material point. Yeah, as we had discussed, right? There is nothing called literally. There is no material point.
okay,
So it's why we call it material point is so just taking a little digression here. So this very subject of study, right? The quantum mechanics.
mm-hmm.
The quantum mechanics tends to apply. So it's
Okay,
rather it's an application. It's the subject which focuses on application of real analysis
okay,
to this to mechanics. So all the things that can be derived of whatever tools were developed in real analysis and function analysis, and that when we apply to uh, that applied to mechanics is called as continuum mechanics. So only if the material is assumed to be continuum, then only we can invoke all those ideas of continuity, differentiability, rate of change, points, sets. Otherwise, the thing is, if we take the material to not be continuous, then the thing is, then we have to model any body in terms of infinite number of points, isn't it? Like small masses at a very atomic level. But the thing is, then the only thing is those. But what we see is the materials at such a level tend to have some sort of a very organized behavior, isn't it? So if some particular body has such an organized behavior, so it looks like there is no discontinuity between any two nearby points in that body, isn't it? It looks like everything is very much synchronized. So the thing is, it's as if what we do is we have started with infinite number of particles, and then we are bringing the distance as close till it becomes zero. I mean, mathematically speaking, that till it tends to be zero. In that case, so the what you call the behavior of the entire set of particles becomes as if it has become some sort of a continuum like it shows continuum like behavior. The thing is continuum, that's an approximation, but this approximation still what you call very much is able to be verified experimentally, and we can, I mean, all the theories that are developed can we can test it also that, and we see that it
Yes.
matches very well.
That's okay. That's okay. Okay. That's true. I mean, yeah, it's continuing. I mean, we have to have this
Yeah.
continuity and all the conditions are
Uh,
described. Also, the point is, since integral equation we're writing a surface integral, the
mm,
point is when you have forces acting on a
mm,
point.
mm,
I mean, we never discuss the angular momentum. If you are applying force like this, right? Take a body, take a
mm,
box, fluid
mm,
block, apply
mm,
forces.
mm,
You never consider the rotational motion induced because of these forces, and I know that because the equal and opposite they gets cancelled. The stress asymmetric
mm,
stress tensor, the one Cauchy actually proposed, and we have axis antisymmetric as well. There's a few the
mm,
new formulations are there.
mm.
Um, that's what I mean. Like that's what the question I always have. Like I know it's continuum, but we take a box of
Mm,
fluid block inside is continuum, and
mm,
we are deriving all these equations. And
mm.
suddenly, sometimes we discuss material point, and it's just
Okay, okay. For the, I mean, material point is what you call more like just idealization of a idealization
block
of
of
small blocks, as if the dimensions of blocks is tending to zero.
okay.
So that's why it's so it means that any it's we represent the properties of that entire block at just one point. The thing is,
Yeah. No, it's
isn't it? The thing is, had it been actually a material point, right? Had it actually been a point per se, if it really were a point, then point does not have density,
exactly.
isn't it?
That's yeah.
So
You can't put a
that's the
point.
first thing that comes
Even in
into,
real
isn't it?
field, you can't put a point. You put a point and zoom it.
Yes, yeah,
It's like infinite, right? You can infinite number of
yes,
points
yes,
in
uh-huh.
real line. The way
Yes,
you
yes,
zoom in, the last time you discussed, the more you zoom in, you have
right,
points and
right,
points.
right. Yeah, yeah, yeah.
Okay, and I think yeah, this is something I
Yeah,
always
so
discuss. Okay,
yeah,
okay,
yeah. So that is where we
continue.
just it's yeah. Now from Cauchy's stress principle, the thing is what Cauchy's aim was to do is he wanted to relate that whether traction can only exist on the surface. So uh, Cauchy's question, yeah, it was does traction only lie at the surface? So has traction to be always external?
Mm.
And if it's not like that, then can we relate? Can we have internal traction? This was the idea that he was looking for actually. So does the traction lie only at the surface? Can we have internal traction? How are they related? If it exists, how are they related? So this was what he was looking at. So it seems that yeah, finally he realized that okay, yeah, traction can also exist within the body itself. Then we have to so when we talk about traction at the surface, so this is a traction at the surface. Say we are applying some traction here, isn't it? The traction surface is how the boundary or how the body interacts with the surroundings, or how the surroundings affect the body through its boundary. That is known as that happens through external traction. Internal traction is how does so if there is some track. I mean, say we are looking at what we usually say, right, in soil mechanics, that we have a body we just cut into two parts, isn't it? Say multiple cuts, and then it becomes, so this will become, one will be this part, there is this part, isn't it? This is what is seen here. This so this face was before, I mean, attached to this face. So we have body. So this was one single body before, but making some virtual cut. This is now body one and body two. But yeah, B1 union B2 is B. That is there. So now the thing is, now there will be some traction also here on the surface, and there also be opposite to each other, opposite in direction but equal in magnitude to each other. So this is traction T vector, and there is also traction T vector, but they are opposite in nature, however equal in magnitude. So the thing is, we also have internal traction. So internal traction is how one part of the body affects the other part of the body for a particular cut. So you say that at every point you can make multiple such cuts with multiple orientations. Say this cut had some normal vector n vector, isn't it? And say if had we made some different cutting, some cut at a different angle, say like this, then you'd have a different orientation of the cut of that cut surface, isn't it? So, and in that case, again, the direction of the traction would have changed. You see, right? Isn't it? So in this case, it was this. Had we made the cut in this fashion, then the traction would have acted in a different direction, the opposite side. So it means that what he concluded was, okay, the first thing is that the traction happens to be a function of, for a given point, traction happens to be a function of
Normal.
normal vector. That's the first. Second thing is, you will have traction. Traction will be different at different locations. So which means that combining both, you have traction is equal to T x with T. So it's a space. It's a function of space as well as the orientation of the cut section, isn't it? So that is what is. I mean, this is what was the conclusion of his stress principle, or the what you call Cauchy's stress principle. And then based on this he realized that at the surface, he said, he realized that at the surface you don't need to make a any cut, because it's, so in that case the traction from one end will be the traction which you are imposing at the boundary. So say you have this body, and you have, this is the traction. Say this is the area that you are, and assuming that there was some cut, just some virtual cut, you just assume it, and you see that there is some, so so the thing is, you are applying some external traction here, so there will be some reaction also from the body side, isn't it? So in that case, the traction happens to be equal to that of the applied traction at those locations, or on those patches.
I
So
think
that
I
was
think
his
I think this is this is like very much similar to Newton's third law, right?
it's
You
it.
apply a
So it said
force,
that
it
Newton's,
is also applied equal and opposite force.
exactly, so it said that Newton's law of this third law is actually special consequence of I
Cauchy's
mean,
stress.
I mean, if we go by ideas, then it is Cauchy's principle explains Newton's law of motion. So it looks like it looks like Newton's law of motion is a consequence of Cauchy's stress principle, not the otherwise.
Wow, that's great.
So yeah, so then he derived some important relation, and the most one of the one relation is that, say, traction for a given point in a different direction is equal to minus traction of x vector. So you see that if you change the direction of, if you just what you call alter the direction diametrically opposite of the normal vector, then you are just it's equivalent to just changing the direction of the traction. So this says one important thing. So this tells us one very important thing. It's known as that traction vector is linear in n vector. You see, right? Because t of x vector comma minus n vector, that just this is equal to minus of the traction of x vector n vector. So it means that there is just a linear relationship. You are not audible. I think you have muted. You have muted.
Sorry.
Yeah.
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 So when you say linear, it is also the main condition is x plus b, t of a
Yeah.
n plus b has to be equal to a times my
Right.
t.
Right.
I mean here it is like -1. So ax is solved, a n is solved, but
Right.
plus b.
Yeah.
Plus
That also.
n. So how? So it is like plus. I think it should be like plus fraction of that.
Okay.
Right? That's what how linear it is.
Uh-huh. So like this
Like
one is
now we want to prove that since you said
uh-huh.
it is linear in n. Now you take a n1 plus n2
Mm-hmm.
t of x comma
Okay,
x
just
comma
let's take
a
here something like
a n1
uh,
a n1 a
okay,
scalar.
let's take something like this.
Let's
So
take
is it
a n1 a times n1 take a times n1.
okay, got this is
No worries, anything is
A,
fine. Yeah, okay, that's good.
A
Now this should be
and
equal to
plus B.
a
Okay,
b.
okay.
Okay, that's fine. Anything is fine. Yeah. So a times t of n1 plus just no remove b because b is more complicated. T times
Yeah.
x comma.
The thing is, I think I think this can be proved by taking what do you call such cross sections, right? You take cross
Yes,
sections
yes,
virtual and then try to take the
that is
sum of
true.
both
That is
and then
true. At a point you have
yeah,
to different normals and the force is equal to
yeah.
the.
Then it's more like
That's
vector
correct.
addition
That's correct. That's correct. That's correct. That's right.
because
I
traction
think
vector is
no. I
a
think
full-fledged vector. Yes.
it's correct. I think we haven't defined how T is exactly. I think we will define now because now we will say that Cauchy said that T's can be defined as sigma ij, and you define sigma. Then when you multiply
Yeah.
sigma times n1,
Right.
then
Right.
then since you take sigma to be symmetric and all that stuff, then it will
Yeah.
automatically be solved, right? Because we don't know how T
Yeah.
is defined. We're just saying that this property is defined. Now we also want it
Right.
to be linear. Then you define sigma
Uh,
related to T. I think
Yeah. Then actually it all boils down to taking different values of, and the thing is you can have infinite possibilities for n.
yes.
So what we do is why not take some standard n's. So then for that case, a very simple model is taken to be a, let's take some unit cuboid and let it orient along three different directions. So this is say E3, E1, E2, and isn't it? Now for every E1, so like this face has a unit vector of E1 vector, and this face has a unit vector or normal vector of E2 vector, and this face has a E3 vector. So for every corresponding E1, you find one T vector, isn't it? So this for this face, and this is a very small cuboid. So in that case, the traction over the entire face will remain single value. It's just a constant vector, isn't it? So in that case, it's just so we just determine say T vector in terms of, and let X vector be the center of this cube so that we don't have to worry about. So it's like X vector is fixed. So all that we need to worry is T vector as a function as in for even for the face with even vector as the normal, and this we linked it to what we got that one, right? E1 sigma 1 1
1
E1
1, yeah,
vector plus
yeah.
sigma 2 1 E2 vector plus sigma 3 E3 vector. So and likewise for E2 as well.
I
And
think sigma first index is is the normal to the plane, and the second
no,
index
the
is the
thing is here
direction.
sigma, yeah, the thing is here sigmas are just projections of T vector corresponding to that face, tractions on that face with respect
Ooh.
to, yeah,
Okay,
that's how
so
we
so
define
sigma
sigma.
sigma one is fraction of, I mean the
Component
t's
of
component in
traction,
one direction. T's
yeah,
component in one
yeah,
direction.
tracks.
Even.
It's the component of traction T vector
It's a t dot
on
t dot
even.
n1 t dot e1, right? Sigma one
No,
is t
it's not
dot
dot
e1.
actually. It's just the T for even T vector for
That's what, right?
surface with, yeah.
Exactly.
So
So
it's
you
like,
have t. Okay.
traction vector for the surface with normal vector E1.
I'm just wondering if I can take the, you see it. Can I take it like that? I don't think we allowed that.
Okay, something like this. Something. Let me just let's just talk about this. Something like you have this face whose normal is
E1.
E1,
Okay.
isn't it? So I'm just taking this face here, dragging out here, and the traction will be some in some other direction.
Yes. And the sigma one is equal to.
Yeah,
Uh,
the projections here, projection.
yeah, that's why I said t
Yeah,
dot e1, right? Sigma one is t dot
yeah,
e1.
yeah,
Right?
yeah.
That's what
Sigma
I was
one
saying.
is T dot E1, and sigma 2 1 is
Two one is
T dot
t dot e2.
E2.
Okay.
Yes,
Okay. Cool. That's
and
what I was saying.
likewise for all the other three
Correct.
faces. So based on this, we have able to now we see that okay. So the thing is now we see that traction for every in every direction is equal to sigma vector plus n vector. So this is the ultimate that the result that comes out from here,
Correct. Correct.
isn't it? So this is the goal here, just to determine T vector in terms of, so the traction is defined as sigma vector dot n vector. So it's like there's matrix into vector product. So that's why the traction comes to be a vector. So the thing is sigma, then you realize that, okay, sigma is not some quantity, it's more like a mapping. So sigma maps normal vector to its corresponding traction vector. So that is the job of sigma. Sigma is more like an operator. However, the good thing about sigma is sigma does not care about n vector. And that's the reason is sigma is again is this sigma also happens to be invariant with respect to coordinate system
Okay.
because it's just a mapping. However, to represent it, you need some basis, and we usually use the canonical basis, which is E1, E2, E3. So that's essentially the goal of sigma. For now, we don't know whether sigma is symmetric or not. Right now, we don't know anything about sigma. We just know that sigma is a second order tensor. That's it. For now, that's all we know about sigma. It's just a second order tensor. That's it. Now, so with this, what we have is from the Cauchy stress principle, we are able to arrive at this very significant result. And we go back and put it here. Here, isn't it? In this equation.
It's t1. Okay.
And then here, once we have, then we'll have sigma n ds. And now you see, right? Now it looks very much like, it looks that there is some, there is some surface integration going on here, isn't it? Because of which we are easily able to use that Gauss divergence theorem, and then this gives us divergence of sigma. And based after using all this, then we have the nice expression v dot dv is equal to rho b vector dv plus divergence of sigma dv. And now we see that bringing all the terms and then localize using the localization theorem, then we have rho v dot is equal to rho b vector plus divergence sigma. And this is the what we call as the Navier-Lamy equations, isn't it?
Conservation. Okay. Yes, Lamas. Okay.
This is the famous Navier-Lamy equations. Now, and the thing is, Navier-Stokes equation is only defined when if the fluid is Newtonian. Till that point, it's just Navier-Lamy equations.
Naval is like very general, even applied to solids.
Yeah,
And
it's
everywhere.
a
Okay, we
yes,
should
yeah.
more say it as Naval Lamis.
Yeah, because it doesn't care about, as of now, it doesn't care about
I
the
think it's like
specific.
conservation of like people. I mean, it's just the first time I'm hearing it is called as Naval Lami. I usually hear as conservation of momentum, so apply it for solids, fluids,
Right.
anything.
Understand.
Naval Lamis is what.
Hello, Dinesh. I'll just come in 1 minute. Some
Yeah, no problem. No problem.
Flipkart guy has come. Yes, just 1 minute.
No
Yeah.
problem.
Hello, Dinesh. I'm back. Yeah, I got late. Sorry. Yeah. Yeah, we were so in this Naved Lame question, right? Yeah. So the thing is here, it doesn't assume any particular form for sigma in this equation here. And that makes it very general, like this. Having no particular form for sigma makes it really general, so that it's here. I mean, it doesn't depend whether sigma is symmetric or not as of now. Now what we'll do is we'll go to the third third conservation law, which is balance of angular momentum.
Krishna,
Yeah.
shall we stop in like 15 minutes if you don't mind?
Sure. Yeah,
In only 15 minutes because I'm like focusing a lot and my eyes are like okay. 15 minutes.
nice.
I think I think today's schedule was to discuss. Uh, uh,
Yeah, the thing
I
is,
have seen you
I
even you have
hardly have.
virtual work as well. Like
Uh,
you have added what
yeah,
all
yeah,
is
yeah.
there to discuss? Show me.
Yeah, there is. We had some virtual work also.
Yeah.
Superimposed
So
rigid body mass objectivity.
did we discuss Cauchy stress principle? No.
Yeah, just now, right? That was
Okay,
the
so that is
Cauchy
covered
stress
now.
principle.
Okay, so we
Yeah.
will discuss angular momentum now. Then you have
Yeah.
3, 4, 5. Okay, we will. Okay, it's a lot,
The
man.
thing is, four is nothing. Four is just remove the time dependent part, and then
Okay, so
that
say
is just
study
different
study
equations.
body, then just write an
Yeah,
answer.
just the steady state part.
Okay, so we
Yes,
can tick it off as well.
right.
Then
The thing is, principle of virtual work is will require, maybe we'll continue it in the next lecture as well. We'll just
uh,
maybe we'll start in the next.
so
So right
no, no,
now,
I think the third the third concept is really interesting. I want to. Is it discussed as well? No, no.
yeah, this is really a very important concept. Yeah,
Yeah,
objectivity
actually.
and
So we'll discuss angular momentum and superimpose rigid body motions and we'll stop there. Next week we'll
yeah,
go
yeah,
to virtual
that's
work. Is that okay?
yeah,
Alright,
that sounds right. Yes, yeah, yeah.
take your time, yeah.
Uh-huh. So in balance of linear angular momentum, what we do is uh, we will what here from the what we call the previous slides, right? We had I is equal to uh, d
Integral rho v dot
rho phi dot, isn't it?
v dot sorry.
dv. Now we see that what we do now is we'll just take phi is equal to
R cross v.
yes r cross v. R is with respect to some origin, so maybe
Okay.
just the origin of the reference frame into v vector. So
Okay.
the thing is, this I mean, as we had mentioned, I mean, we talked about some time back that what do you call di by dt just gives us that rate of change of that particular quantity just within that particular body. However, that change has to be brought by some external factor again,
Yes.
isn't it? And then this is what we call as m external, and m is what we call as momentum. So, sorry, moment, the externally
Yes.
applied moment. Now
That is
it can be yeah, and it can be composed of two parts. One is fully volumetric again.
body and surface forces as we know.
Yes,
Yeah.
again,
Just
yeah.
b
What
cross R cross b
just yeah,
cross rho b dv
plus
integral
R cross
t R cross t
T at TDS, isn't it? And this is at over the
and
surface.
ds. Since t can
Now
be
the thing
written as
is,
sigma times n.
yeah.
I'm
Okay,
just
and
rushing.
then
I'm sorry if I'm rushing. So
no, it's all right, Yeah, after that,
let me
what
know that.
what we have is then it comes to be after we put here, then we have rho R dot R cross V dot V, isn't it? dv
Right.
is equal to, and then in this case also we'll have a similar thing. So R cross V vector dv plus here also we'll have uh, let me do now parser and R cross sigma and ds. Now what we do is this one will use Gauss divergence theorem for the last term and the first term, and the term on the right left let's use a chain rule. So it becomes rho r dot vector cross v plus rho r cross v dot vector. Now you see one thing, right? In this term here, this term. So this term r dot is nothing but v itself.
Yeah, so that is 0.
Yeah, so this term becomes 0.
Like it becomes 0 and you have only r cross v dot.
Yes. And on this side here, r cross rho b vector dv plus. And now we can use Gauss divergence theorem for this term.
Yes, that
So it
becomes
becomes,
r cross divergence of sigma.
yeah. So divergence of this quantity.
Sorry, yeah.
Something like this, yeah. And the thing is, it can act on both. So what we'll do is we'll we'll allow it to act on both. And
so we
we'll
take
have
quantities and that's right.
Yeah, r cross, and then we'll have to use what do you call that, chain rule again, and there's already b. So divergence of this one cross. So divergence of cross plus.
N as well.
So that is actually subsumed because we use the Gauss divergence, right?
Correct.
So we used Gauss divergence. So this one was Gauss divergence 0. Now what we'll do is, now let's do one thing. So now let me just copy all this here, because this is the most
divergence of. Okay.
The thing is, by this point, by this time, people actually all the books and all, right, they just switch to indicial notations.
Okay.
But it's what you see is it's things become more. I mean, the flow is intact if we proceed the way we are going now.
Okay.
Now what we do is let's bring all the terms on the left. So we'll have r cross rho v vector dot minus rho b vector minus divergence of sigma dv, and keep only one term on the right, which is
Okay.
divergence of r cross sigma and dv. Mind you that the thing is, I have never expanded it like this. I'm just trying to just see that how it comes out in this form. How does it look like?
Interesting. Yeah,
Just,
we'll do that.
just trying to see it, because the thing is, it's not consistent here because this divergence will lead to scalar, and so it's just trying to just capture the idea, because we have already done so many times in indicial, right? Let's see how it looks like in vectorial notation, how things look like. Now you see one thing, one interesting thing here. What is this integrand here?
Oh, is that momentum? Yeah, it's momentum.
Yeah,
Momentum observation. Yeah,
yeah,
interesting.
yeah.
Yeah.
So this becomes 0.
0. Yeah.
So whatever the thing has comes only from this side now. So this becomes 0.
So it doesn't matter what kind of sigma we are dealing with, like symmetric or not symmetric, right?
Yeah, right now.
Yes.
But
So the
after
conservation.
this, yeah, conservation of linear momentum doesn't care about the nature of sigma.
Okay, it's interesting, man. Okay.
So here, actually, then this particular term becomes 0. And this actually implies that sigma is equal to sigma transpose. When we do something, when we do some what do you call industrial expansion, right? Then we are actually able to get the sigma is equal to sigma transpose. This is the consequence of this, because all the terms on the left has become zero, so it's only this remains.
So the only so this will be zero only when sigma is sigma transpose. Is that what the conclusion is?
Yes, right. But this one doesn't need any constraint on sigma. It's only for this thing to be zero always. You need to have
Okay.
sigma is equal to sigma transpose. Now you say fine, but when is the situation when sigma is not equal to sigma transpose?
I don't know. There is some like some materials where you have this property where sigma is not sigma transpose, right?
The thing
I,
is, we
crystals and stuff like that. I think that's where I hear a lot where sigma is.
the thing is you have to go to the previous slide again.
Okay.
Now let's look at our what all contributing factors did we include for external moment. Have you do you notice anything new? Nothing, right? It's just
That's what. That's what.
this
I'm
one
like,
is
confused. Like, where did we go? Like, what actually happened? Yeah, background. Yeah.
see. This is just due to moment due to external work and external that body force. This is due to external tractions.
Correct. Correct.
There is something missing, isn't it?
I don't know.
Yeah, there is where we actually the thing is, what if there is some external moment,
Oh,
what do you call it?
okay. So
External moment?
just like external moment, not due to the moment, due to tractions. Just like forces, you
Yeah,
have external moments.
yeah, exact the actual external moments, not just the moments due to all that arms
Okay.
taking
Only
arm
in
and
that case you don't have sigma to be equal to. Okay.
right.
So I think
So that
the way to look at this is like you look at the behavior of the material first, then
huh,
you will do some studies,
hmm,
then you will conclude with sigma. It's not the other way around, right? So now, since if you see external moments, then you will
huh,
say no, sigma can't be sigma transpose. You have to have sigma
huh.
to be something else. If
Yeah, the
if you
yeah,
consider if you see the real behavior, you will outline it. Then you conclude okay, sigma can be sigma transpose because you don't have any like like external moments and all that stuff.
yeah,
That's how
there
you
is
have to
no.
derive. Okay.
Yeah, because the thing is, we have already taken only those. We have taken moments due to forces, not
Correct.
true moments. So for that, we need to include one another term, and I'll just use in a different color. Let it be in black. For that, you need to have pure moment. So that is like rho into c vector.
Yeah.
So this is the actual pure momentum, pure external momentum. You see, right? There is no r vector coming to the picture. So which means that there is no momentum coming to the picture. And this one is due to things like electromagnetic couple.
Oh, you deal with this stuff actually.
Yeah, so
You
it's
have
like
this in your
electromagnetic couple, and all those very artificial couples that you can have, isn't it? Like apart from, I mean, electromagnetic is in general, I mean, it's fundamental coupling. I mean, it has this. So it does is, you see, right? The C vector is a vector field. C vector is a vector field. It's a function of space and time, and this is actually C vector is a moment. So it will have all that. So the thing is, it will induce moment like this, but the direction is vertically outwards. You see, right? So it's let me have in counterclockwise. So it will. So the vector acts. So the direction is vertically upwards. However, all it does is it creates local small moments. So it's like atomic level moments. Now you see, okay. Now you'll see that fine. And let just carry on this term to all the throughout our derivatives. So let's put it here as well. here as here as well. Now you see, now we notice a very interesting thing going on here. That no matter whatever the term with sigma was, there is also this term added.
Mm.
Then it comes to this one. Now, and then we can add all of them. And now we clearly see that sigma is no longer symmetric. After using all this localization theorem and all that, sigma is no longer symmetric. But because there will be sigma symmetric part if we say. So I mean, like, so sigma will have some part plus c, because c is pure moment. So c is pure moment. So what we have seen is, isn't it? So what we have seen is that now the complexity has increased much. Now all those ideas of symmetry, I mean, sigma always coming to our rescue due to its nature of symmetricity is gone. So that is one example of when sigma is not symmetric. It's when we have electromagnetic couple in the system or any such coupling, even if we have, say,
Yeah.
dipole like coupling, electric dipoles.
Yeah.
So
Clear.
all that, because of it, then there is where that. So yeah, this is where the thing is, it people usually, I mean, you'll see that they will discard it here itself, that they won't take any pure couple. They will only take moment due to external loads and not pure couple. Only if we add pure couple, then we see that. So the thing is, this is the more general case. So for pure couple, I mean, what we could have done is just at the end, we could just have taken C vector to be zero, just to say that, okay, in the absence of coupling, we'll have electromagnetic couple or any special couples, we'll have sigma is zero. Otherwise, the form of sigma will be nothing. So that was the idea that we were looking for. And about objectivity, let's talk a little bit about objectivity. The
Discuss.
thing,
I mean, we'll stop it here. What do you say?
yeah, that's also fine. Objectivity is somewhat, yeah, very subtle to
No, it is
understand.
very important. I think
Yeah,
objectivity, I see it all the time. I mean, there is
yeah.
this big chapter in some books, like
Right, right.
fully about objectivity. I
Yeah,
think
of
objectivity
the,
states that even you rotate the bodies, it's just
uh,
something, right? You're looking
yeah,
at it with different
right.
coordinate system.
There it
See,
involves both actually. There it involves space, I mean, rigid body motion in space and translation in time. So the thing is, a constitutive models, I mean, the state of the deformation of the body or the deformation measures of the body and also the strain measures of the body should be such that even if we rotate the body, if even if the perform something called as rigid body motion on that body, and even if we proceed in a different coordinate system where even we just shift the time, isn't it? The stress states should not get changed. So that is the idea of objectivity. So I'll just in a figure, let me just draw a simple figure. We will not go into math, just a figure. So you say you had a body here. This is B naught. So this is like undeformed body. Gave some deformation side. Then this becomes
okay.
B.
So are you discussing it now?
Now this is just we'll just discuss the idea. We'll not talk about maths.
Okay.
Just the idea. Yeah.
Yeah.
And say we have just given a rigid body motion. So the thing is
Okay.
this B and this B star. So this only shifts by rigid body motion. Isn't it? This is just like rigid. So the thing is stress measures and strain measures should in B should be the same as stress and strain measures in B star. How does this look like? This looks like as if you have one observer here. So for an observer, when an observer is looking at this body here, at this at the body, the deformed body, and for it, it doesn't. It's able to measure the same stress and strain measures in this as well. So that is the idea of objectivity in the sense that any rigid body motion in space and time translation.
Okay.
Which means at what point did he look at the same body? Should not alter or should not what you call interfere with the recording that he has. But
Yeah, so the sigma has to be same, even though it
yeah,
is
has to be the
the
same.
same as in you have to see. Like it should only have the coordinate transformation. It should not give additional strain for us, right?
Exactly.
I think we should discover strain now. Like the
Right.
stress values will change,
Yeah.
but because coordinate is changed, but the strain
Yeah.
value has to be same. I mean, the strain
Right.
body is only rigid body
Strain,
transformation.
stress, all of
You
those
will,
quantities
yeah,
should remain the
you will do something and then you move it. The
same.
strain is same, but because we have moved it, now I'm studying differently. The strain should not change, right? I mean,
Yeah,
that's
yeah,
the
yeah,
idea.
yeah.
Okay.
That's how it is.
So
Yes, yes.
can you go back to the objectives once, please?
Which one? Which one?
The objectives first slide we discussed
Okay,
now.
okay, okay. Yeah.
So we have done first one, second one, and fourth one. So we will do third one and fifth one.
The thing is, yeah,
So there,
fifth one actually required a complete lecture because the thing is,
oh,
I don't know why why he just did, why the professor, the instructor, why he did it in just spend one small amount of time and then just
okay.
zip past as fast as. But the thing is, principle of virtual work is
Yeah, correct. That's right.
ultimately is the foundations of finite element methods, isn't it?
Correct. Yeah.
So there was a
So
sudden jump as I was going through his lecture. There is just a sudden jump from
okay.
what he has done,
So
and then he jumps into virtual without even giving the basics as to why it came, how it comes, and so yeah, that's the thing. The principle of virtual work ultimately is all concepts derived from variational calculus, right?
yes, exactly. That's
Yeah,
what I was saying. Like
yeah.
if you know principle of virtual work, it also goes to mechanics, classical
Uh-huh.
mechanics.
Right,
It's all
right, right.
virtual Hamiltonian,
Yeah,
Lagrangian
and
mechanics,
all that, even
Newtonian.
this
Yeah,
Castigliano principle and all,
exactly.
Castigliano's theorem and all,
Yeah,
it all involves.
yeah.
It's all based on principle of virtual work. Yes.
Virtual. I think so. I think we can do this next week. Next week's
Ah, yeah.
tutorial. I think after this, so when will we discuss the pre-allocate of test trends of the stuff? When will we
Which one is?
pre-allocate of pre-allocate
Okay,
of
that's coming in the next lecture actually. Yeah, yeah, it's coming in the next
I
week
think
now.
I think next week we will complete third and fifth quickly, like in 1 hour, and in the other 1 hour we will discuss the whatever the week this week lectures are.
Right, right. Yeah, that's true.
Like
That's
that
true.
should be
Yes.
good.
Yeah.
I think we
Yeah, yeah.
because this week we again revised conservation of mass. We took some
Right,
time.
right, right,
Next
right,
week we will
right.
quickly start and
Yeah, yeah,
just bang
that's
it.
true. Yes.
Great.
Yeah.
Okay, awesome,
Okay.
awesome.
Okay, Dinesh. Yeah.
Enjoy. Have a good day.
Okay, yeah. Thanks. Yes. Yeah.
See you.
Yeah. Okay, so let's meet next week. Yes.